Hello, everyone. Hello, a very good morning to all of you. Am I live? Let me just check if I'm live or not. Hello, everyone. Hello, a very good morning to all of you. Am I live? Yes, so I am live, I think. Yeah. I hope I'm clearly visible and audible to all of you. So, a very good morning to all of you today. And I hope your preparation for your re-NEET exam is going good, and you are able to focus your energy and focus your mind at the revision for your exam, right? I know you must be very stressed as well right now, but just keep faith in yourself, just trust the process, and I'm 100% sure that all of, like, everything will go good in your exam and you will get the desired results. So don't worry at all, right? So let's begin our today's class. In our today's video, in our today's class, we are going to complete the revision, right? So we yesterday started the physics revision. So in the yesterday's class, we revised all the chapters of our class 11th, right? And today we are going to start with the class 12 syllabus, right? So we are going to start with the very first unit, that is electrostats, then electrostatics, followed by current electricity, and so on, right? I hope all of you must have already, revised all the concepts once, but this is a final revision marathon. And what I'll do is, because you also obviously know that we can't, really discuss everything in depth, in detail right now. So what I'm going to do is, I'll discuss the small things slightly in detail. And apart from that, the direct things like application of Gauss law, we are not going to discuss the process. We are just will just revise the formula ones from the point of view of your numericals for the re-NEET exam, right? So for the physics section of your re-NEET exam, you just have to remember two things. All the statement based questions, assertion reason type questions, they will be on like theory based. And from my experience, I believe that the numericals won't be too hard, numericals won't be too easy. They will be somewhat in the middle. And I believe that like, out of the total number of numericals, around 50 to 60% of the questions will be directly formula based, and the rest remaining numericals will be slightly like connecting two or three chapters together, connecting the using the formulas from multiple chapters, those type of things, right? So for that, you need to remember all the formulas very carefully. So let's begin with our very first topic, right? So our very first topic is going to be electrostatics. Just. So our very first topic is going to be our electrostatics, right? So within electrostatics, we will see. I'll just, yeah. So our very first chapter is going to be electrostatics. I think there is some problem. Let me just restart this. So till the time the application is restarting, so electrostats was basically the study of charges at rest. And then we studied a few properties of charges. So as we know, charges are of two types, positive and negative charge. And then like charges will repel each other, opposite charges will attract each other. The charge on any body will always be quantized. That is, like, it will always be an integral multiple of charge on one electron. That is, the formula will be Q is equals to N times E. Yeah, so now it's working. And we will start with our first topic, electrostatics. Yeah, so for your properties of charges, so one of the properties was quantization of charge. Quantization, the formula for quantization was Q is equals to N into E. E is the charge on one electron, and the value of E is 1.6 into 10 raised to the power minus 19, right? So this was quantization of charge. Then there was other property which was additive nature of charge. That means the charge can be added together or subtracted, right? Subtraction will happen in case both the charges are of opposite nature. One charge is positive, other is negative. In that case, subtraction will happen, right? So these were the two main properties of charges, and the last property was that the charge is always conserved. Like, the charge will not be lost. It can only be transferred from one body to other, but it will never be lost. Similar to the case of, like, law of conservation of energy, right? Then our second most important thing, from here you will, I believe you will get a question, a numerical, that was Coulomb's law. So Coulomb's law basically told us the force acting between two charged particles. I have a charged particle Q1, I have a charged particle Q2. What amount of force will Q1 apply on Q2 and Q2 apply on Q1, right? So the formula for force between these charges was K Q1 Q2 by R square, where the value of, like, we can calculate K by, K was equal to 1 upon 4 pi epsilon naught, and then the formula became Q1 Q2 by R square. K Q1 Q2 by R square, that is 1 upon 4 pi epsilon naught Q1 Q2 by R square, wherein epsilon naught was relative permittivity of free space. That means the value of epsilon naught was different for different mediums, right? Epsilon naught was basically the permittivity in free space or vacuum or air, and then if you put the whole setup, put all the charges in some medium. So in case of medium, what changes was, you will see a extra term along with epsilon naught. The formula now becomes 1 upon 4 pi epsilon naught epsilon r. Epsilon r was the relative permittivity of the medium. For example, the question might say that a setup of two charges was kept in air, and they were experiencing a force of 20 Newton. And then the complete setup of charges was kept in water, and the relative permittivity of water is 80. So then you have to calculate the force acting in the water. So always remember that force in medium is always 1 upon epsilon r times the force in air, or I will just write F naught. If you take the ratio of force in medium, let's suppose this is force in medium, this is force in vacuum. So this ratio will always be equal to epsilon, 1 upon epsilon r. That means whenever you put any system of charges in a medium, the force acting between those charged particles will reduce by how many times? By the relative permittivity amount of times. So this was about Coulomb's law, and then you also saw the vector formula for Coulomb's law. So vector formula basically, when you take this R in terms of a vector form, that will give you the vector formula. I'll just write the vector formula also for you people, right? So vector formula can be force vector is equal to K Q1 Q2 R12 vector divided by R cube. So this is basically, you can write it as R12 magnitude also, cube of magnitude, or simply R12. This will be the force acting. So if this is charge particle 1, this is charge particle 2, this side will be R12. So this will be the force acting on charge particle 2 due to charge particle 1, right? So this was the vector formula. Then we saw what do we mean by electric field. So electric field is basically charge surrounding a area surrounding a charged particle in which other charged particle will experience a force. That force can be either attractive or repulsive, but it will experience a force. So electric field was basically force acting per unit charge. E is equal to F by Q, and from here we got a very important formula. F is equal to Q times of E. And direction of force and electric field is same for a positive charge particle, and it is opposite for a negative charge particle. And over here we also discuss the principle of superposition. So principle of superposition, it basically tells us that the total force acting on any particle is the vector sum of principle of superposition. Superposition. So it basically tells you that if this is the charge on which you want to find the net electric field, this is first charge, this is second charge, this is third charge. Net force acting on this center, this charge particle kept on the center, is the vector sum of all the forces acting on this charge particle. This is what principle of superposition told us, right? Then electric field we already saw. So if you just substitute the formula of F over here. F was k q1 q2 by r square divided by a charge. So electric field becomes k q by r square. This is the formula for electric field. Now there were two important graphs. First graph between electric field and r square. Electric field and r square, if you see, electric field is inversely proportional to r square. Just keep in mind that we are taking r square on the x-axis and not r, right? So this is inversely proportional, and then the second graph was for electric field and r. Sorry, 1 upon r square. These are the two important graph. 1 upon r square, you will see this whole thing is electric field is directly proportional to 1 upon r square. So that will be a straight line graph. Then there were electric lines. So electric field, we can basically represent electric field around any charged particle using electric lines of force, like electric field lines. There were some properties of electric field lines. We'll just discuss them verbally. So first of all the electric field lines will always start from positive charge particle and end at a negative charge particle. Secondly, no two field lines will ever intersect each other, because if two field lines intersect each other, then at the point of intersection, you will get two directions of electric field, and at a single point field can only be in a single direction. So this is not, so intersection is not possible. Then the next property was that the closeness of field lines will actually tell you the strength of electric field. Closer the lines, greater is the electric field intensity in that area. Farther are the lines, lesser is the electric field intensity, right? Then the last property was that the tangent to any point, for example, if this is the field, then tangent, I want to find out the electric field at this point, I just need to drop a tangent to the electric field line. Tangent to the electric field line at any point will give you the direction of electric field at that particular point. Field line is basically describing the field in a particular area. But if you out of that area, you want to find out the field at a particular point, then you need to use the tangent, right? So electric field lines, you should know for a dipole. So for a dipole, electric field lines look somewhat like this. Some field lines will enter from positive charge to negative charge, and then some of these field lines will not be able to enter. Sorry, arrow will be outside, right? So this was a field for our dipole. Then electric dipole, I'll just change the color. Electric dipole is one of the most important things which you should remember. Why is it important? Because whatever we are like revising right now over here, same things are there in your chapter number 5, that is magnetism and matter. So electric dipole, it is a system of two equal and opposite charges, equal in magnitude, opposite in distance, opposite in sign, or opposite in nature, separated by some distance. That setup is called electric dipole. Every dipole has something called a electric dipole moment, and that dipole moment is equal to charge multiplied by the length of dipole. For example, if I say that this is q, this is minus q, amount of separation between these two charges is 2a. So the length of the dipole becomes 2a. So dipole moment becomes q into 2a, q into 2a. And this distance is a vector quantity. Dipole is a vector quantity, and electric dipole, you just need to remember the direction. Electric dipole is always from negative to positive charge. The direction is fixed. It is always from negative to positive charge. Then there were two derivations. First, electric field at axial point. Electric field at axial point of a dipole and electric field at equatorial point of a dipole. I will first write the exact formulas and then write the approximation. Axial point, this is a dipole. If you take some point at a distance from the center of this dipole on its axis, right? So for axial point, the exact formula was 1 upon 4 pi epsilon naught p 2r divided by r square minus a square whole square. This was the exact formula. What do I mean by the exact formula? We haven't assumed anything right now. But the final formula which we get was under the assumption that if my dipole length is very, very smaller than the distance. R was the distance of this point from the center of the dipole. This was r. If I consider that my dipole is very, very short. Under this assumption, under this condition, my formula becomes 1 upon 4 pi epsilon naught 2p by r cube. So the formula was basically 2 kp by r cube. Similarly, for a equatorial point, the exact formula was 1 upon 4 pi epsilon naught p upon r square plus a square raised to the power 3 by 2. This was the exact formula. Now substituting the approximation, formula becomes 1 upon 4 pi epsilon naught p by r cube. Now if I see both these formulas, I'll see that electric field at axial point is just double the electric field at equatorial point for a short dipole. Short dipole means a dipole whose length is smaller than the distance between the center of the dipole and the our interest point, right? So these were the two main derivations. Then the next thing was our electric field intensity on the point of a uniformly charged ring. If I talk about a uniformly charged ring, the diagram was something like this. We took a ring like this, sent from the center. This is a point P where we want to find out the net electric field distances R. Radius of this ring is A. And then we took 2 points, like two diametrically opposite points, and then saw what will happen. This was the sort of a setup. I'll just write directly the formula. So now the electric field magnitude in this case was KQR upon R square plus A square raised to the power 3 by 2. I'm just writing K instead of 1 upon 4 pi epsilon naught, right? Just remember the value of K as it is. Like most of the times you don't have to, calculate the value keeping in epsilon naught. That will actually lead to a lot of time wastage. So value of K is simply 9 into 10 raised to the power 9 Newton meter square per coulomb square. Okay. So this is the value of K. You should remember this. Then we had, if we keep a dipole in a uniform field, dipole in a uniform electric field. So if a dipole is kept in uniform electric field, then what will happen? Dipole in a uniform electric field. So first of all, we saw the formula for torque. The torque acting on a dipole. You just need to remember, whenever you put a dipole in uniform electric field, a very important thing for your statement based questions, and it has been asked many times in the NEET exam. Whenever you keep it in uniform electric field, it will not experience any force, but it will only experience a torque. But if you keep it in a non-uniform field, the dipole, in non-uniform field, dipole will experience both. It will also experience a force, it will also experience a torque. Okay. In uniform field, no force, only torque. In non-uniform field, both of these things will be experienced, force as well as dipole. Formula for torque was P cross E, cross product of dipole moment with electric field. Or I can also write it as PE sine theta. right? And then we saw three special cases. First, for unstable equilibrium, stable equilibrium, and maximum torque. Maximum torque will act at 90 degree, angle of 90 degree. Stable equilibrium will be when angle is 0 degree. That means dipole and electric field are pointing in the same direction. And unstable equilibrium will be when theta will be 180 degrees, right? So this was about the torque. And the second thing which we saw was potential energy. The formula for potential energy was minus P dot E, or I can write it as minus PE sine, cos theta. Now, many a times you get a numerical for calculating the change in energy. So, change in energy, when does the energy change? When you change the orientation. Like you earlier, the angle which field and dipole moment were making was 60 degree. Now you change this 60 degree angle to 90 degree. Whenever there is a change in angle, what will be the amount of change in the potential energy? So, that formula will be minus PE cos theta 2 minus cos theta 1. Theta 2 is the final angle, theta 1 is the initial angle. So these were the two things which were discussed. Now moving forward, we had, so what I'm going to do is I'm going to discuss the complete electrostatics together. So like I'm not keeping, I will not be discussing it in two separate for chapters, right? Because both the chapters are linked with each other. The next thing which we'll be discussing is potential difference. Potential difference. Potential difference, the symbol is V. Potential difference is simply the, like if you can see, we are the name has difference. Difference is always between two things. So potential difference is always defined for 2 points, whereas potential is defined for a single point. Formula for potential difference was energy, like work done in bringing a unit positive charge from one point to other in a field, right? So work done in bringing a unit charge, that means work done per unit charge. This was our potential difference, and potential was the work done in bringing a charge from infinity to a particular point, right? So this was potential and potential difference, and then we derived the electric potential due to a point charge. What will be the formula for that? So we found out that potential was simply equal to 1 upon 4 pi epsilon naught q by r. If you will notice one thing, first of all, we had formula for force, then we had electric field, and then we have potential. See, these three formulas are linked with each other. How? Force had two charges, q square, and 2 times distance was multiplied. Then you remove one charge from this formula, you get electric field. Then you also remove a r from this formula, you get a potential. Just remember, like, keeping this trick in mind. So this was the formula for potential. Then again, the two graphs which we also saw for electric field. First graph V versus R, and second graph V versus 1 by R. So V versus R, potential is simply inversely proportional to the R, right? Inversely proportional, that means it will look like rectangular hyperbola. And then V by 1 upon R. So this, with both these things are directly proportional. So in case these things are directly proportional, I'll just keep it like this. Just a second. So this will be a simple straight line thing. But just keep in mind that most of the times, like instead of remembering these graphs, you should remember a graph. Many a times, NEET has asked a question that both your graphs were actually given in the same thing, right? This is graph number 1. Draw it properly. This is graph number 1 and this is graph number 2. You need to identify, they will mark both these graphs as A and B, and then you need to identify which graph is for electric field and which is for potential. Always remember the graph which falls very at a fast pace, that is for electric field, because electric field is inversely proportional to r square. The graph which falls at a slower rate is for your potential. Why is the graph for E falling at a fast rate? Because it has a square term, whereas potential has a 1 degree term. So on on y-axis we have electric field and potential, on an x-axis we have r, distance, right? And always remember that whenever your charges are positive, for a positive charge the graphs will be in the first quadrant, for the negative charge graphs will be in the fourth quadrant. Then I'll just draw that graph also, v versus 1 by r. This will be a simple straight line. Okay, but this graph is more important, you should remember this one. Then if I move slightly back, we will write over here only for the potential as well. Potential at a axial point and potential at a equatorial point. What will be the formula? Like before that, we will write the potential at center of dipole. Potential at center of dipole. So potential at center of dipole, you will see that will come out to be 0, right? And potential at center of two equal and like equal and opposite charges, equal and like charges. Like if you have a charge plus q and a charge plus q over here, then at the center of this charge setup, potential will be non-zero, field will be 0, right? So moving forward now, we have a relation between electric field and dv by dr, that is electric field is always equal to negative of potential gradient. That means why does the minus sign is there? Minus sign basically denotes that in the direction of field, potential will always decrease. Whenever you move in the direction of field, your electric potential will always decrease. And always remember that your electrostatic force is a conservative force. Then there was something called as a equipotential surface. Equipotential surface is basically those surfaces at which the potential is equal. Equipotential means equal potential surfaces. Work done on taking up any charge from one point to another. For example, if I say this is a equipotential surface, that means at this point and at this point, at every point the potential is same. I can simply say work done is equal to q into delta v, charge multiplied by change in potential. That will be the amount of work done. Now, if I am saying this is a equipotential surface and you have to take a charge from this point to this point, because these points are on a equipotential surface, potential at A and potential at B will be equal, right? Because the potentials are equal, the change in potential will be 0. So, work done in taking a charge from one point to other on a equipotential surface will always be 0. You just need to remember these things, right? And the last thing, I'll mention it over here only, the potential energy. Formula for potential energy, U. Formula for potential energy was simply K Q1 Q2 by R. K Q1 Q2 by R. These four formulas are the basic building block of both these chapters. Okay. Now moving forward, now we have Gauss law. Gauss law basically stated that the total flux through any surface, the total flux passing through any closed surface. So we saw the formula for flux. Flux is basically E dot ds, dot product of electric field with area vector. Gauss law told us that flux passing through any closed surface will be 1 by epsilon naught times the charge enclosed by the surface. And based on this Gauss law, we had 3 or maybe 4 applications. First was for an infinite line charge. Infinite line charge. For an infinite line charge, we calculated the field. Formula for field was lambda upon 2 pi epsilon naught r. Second, we have a plane sheet. For a plane sheet, if the sheet is thin, then the formula for field was sigma by 2 epsilon naught. If the sheet is thick, for a thick sheet, the formula becomes sigma by epsilon naught, because for thick sheet, the front and the back part of the sheet both will contribute a component of sigma by 2 epsilon naught. So it will get added, and for a thick sheet, formula becomes sigma by epsilon naught. And then third, I had a hollow sphere. Hollow sphere, or if we like, we can call it a spherical shell. For spherical shell, we had 3 particular points. I'll just first make a graph and then explain you, so it will be easier to for like in your revision. So if this over here at this point, small r is equal to capital R, this is my electric field. This is the maximum value. Capital R is basically the radius of sphere and small r is the radius of Gaussian surface. So three possibilities could be that the point may lie inside the sphere, point may lie at the surface, and point may lie outside, right? Surface and point may lie outside the sphere. So inside the hollow sphere, no charge is enclosed. So inside the hollow sphere, field is always zero. Basically, this part of the graph, this part. Okay. So this is zero electric field because over here, this part represents when R is less than R. That means we are inside the hollow sphere. Then the field is maximum at the surface, and then it gradually, as you move outside the sphere, it gradually keeps on decreasing. So for the formula, like at the surface, the field becomes, I'll just write the formula. At the surface, the field becomes sigma by epsilon naught, and outside the spherical shell, the formula becomes sigma upon epsilon naught capital R square by small r square. Capital R is the radius, small r is the radius of our Gaussian surface. That means the point, the distance of our interest point from the center of the sphere. In case of a solid sphere, only one change occurs. This graph remains same, like at the surface and outside the surface, the graph remains same. Only we get a component inside the surface as well, inside the sphere as well. If the sphere is solid, some charge will be enclosed whenever you are inside the sphere. So you just need to remember this. This graph is for solid sphere. This graph is for a hollow sphere. This is for hollow and this is for solid. Okay. Then moving forward, the next thing which we are left with is capacitor. So capacitor is simply, capacitor is basically, or capacitance is basically the ability of a charge, ability of a conductor to store charge. And the formula which relates charge and capacitance was basically Q is equal to CV. C is the capacitance, Q is the charge, V is the potential, right? And then you found out capacitance of a spherical conductor. Spherical conductor. So in case of a spherical conductor, our formula was 4 pi, capacitance was 4 pi epsilon naught r. R was the radius of this conductor. Then we had a parallel plate capacitor. So what we saw, like if you see, if we have a spherical conductor and if we have a spherical capacitor, what is the main difference between a conductor and a capacitor? Conductor can also store a charge, capacitor can also store a charge, but the charge stored by a capacitor, like the value increases by a significant amount. Capacitor can simply hold a greater amount of charge. A same size of capacitor and a same size of conductor. This is a conductor, this is a capacitor. For same size, capacitor can hold more charge as compared to the conductor. Why? Capacitor will always comprise of two conductors or two surfaces at least. Okay. So due to this, you can check. So if I say, like for a spherical capacitor, we will also see for a spherical capacitor, I have taken two conductors. This is a, now this chart, this setup becomes my capacitor. For a capacitor, formula for was for capacitance 4 pi epsilon naught A B upon B minus A. If you see, this value will always be greater than 4 pi epsilon naught. This will always be greater than 4 pi epsilon naught R. Okay. So capacitor will always store a greater amount of charge. Then we had PPC, that is parallel plate capacitor. For parallel plate capacitor, as capacitance was A epsilon naught by D. And simple thing, if you keep this in some, in some medium, the formula becomes, you just need to simply multiply it with the dielectric constant, either with K or epsilon r, whatever is the value of the dielectric constant. Then grouping of capacitors in series, in grouping of capacitors, series and parallel, the formula for resistance, just interchange that. The formula which was used for parallel in resistance will be used for series in capacitance. 1 by Cs is equal to 1 by C1 plus 1 by C2 and so on. For parallel, the formula is 1 by, not 1 by C, simply C is equal to C1 plus C2 for series and parallel. Then we had energy stored in a capacitor. Energy was simply Q square by 2C. We had three formulas: Q square by 2C, half CV square, or half Q into V. This was the formula for potential energy stored inside a capacitor. And however you group the capacitors, either in series or in parallel, the energy will always be a sum of individual energies. And then there was something called as a common potential. Common potential was simply that wherever you connect two charge conductors, they will never ever what do we say, they will never ever divide their charges in half. It's not the case that if the total charge is 10, then both of them will get half charge. Why is that a problem? Because it might be possible that the size of the capacitor is different, and then the smaller capacitor is not able to hold that amount of charge. So what actually happens is they reach a common potential, and that common potential can be calculated by total charge divided by total capacitance before connecting. Before connecting, whatever the total charge was on the system divided by the total capacitance, right? And if I move back a little, we had a another thing which was PPC with, I'll write the formula over here only, PPC with dielectric slab. If we have inserted a dielectric slab inside a parallel plate capacitor, then our capacitance was A epsilon naught upon D minus T plus T by K. T was the thickness of dielectric slab and D was the separation between the plates of a capacitor. Okay. So moving forward now, this was all about our this chapter, this electrostats unit, right? Now moving forward to current electricity. Moving forward to current electricity. So for in current electricity, we started our discussion with, like, I'll just write this chapter has maximum number of formulas and maximum amount of weightage. Current is basically charge flowing per unit time. Unit for current is ampere, unit for charge is coulomb, unit for time is seconds. Then we studied Ohm's law. Ohm's law simply said potential is directly proportional to current. Formula becomes V is equals to I into R. Then we saw the factors on which resistance will depend. It will depend on length and area. Formula was rho L by A. Rho was the resistivity of the wire. Then the third thing which we saw was current density. Current density is a vector quantity while current is a scalar quantity. Current density was simply current flowing per unit area, I upon A. Then we studied vector form of Ohm's law. Vector form of Ohm's law simply stated that J is equal to sigma E. Okay, so I'll write two more things over here. Just we have, like we have resistance, we have reciprocal of just the opposite of resistance called conductance. As we have resistivity, reciprocal or opposite of resistivity is conductivity. That means 1 by rho. Resistivity and resistance tells you the amount of resistance offered or the amount of opposition offered. Conductivity or conductance offer you the amount of support offered, right? So this was vector form of Ohm's law. Then there was a discussion about drift velocity and we derived the formula for drift velocity. Drift velocity formula simply came out to be E tau by M. E tau by M. And then we had relation between current and drift velocity. I is equal to NEAVD. One of the most important formulas and most used formulas. You will get a direct numerical from this formula. Direct numerical. Just need to remember the formula. Okay. I is equals to NEAVD. Then there were two things which we derived using Ohm's law, the formula for resistance and the formula for resistivity. So formula for resistance was ML by NE square tau A. Formula for resistance, resistivity was simply M upon N E square tau. If you equate it by rho L by A gets cancelled and the term which is left is simply rho, right? And then we discussed about mobility. Mobility was simply drift velocity per unit of electric field. Drift velocity per unit of electric field. And we saw that charge carriers can be primarily two things. First, it could either be an electron. Second, it could either be a hole. In case of electron, in case of hole, what hole is specifically? A vacancy created by an electron, that is a hole. And as we already know that electrons have a greater mobility as compared to holes. Then we saw temperature dependence of resistivity. For temperature dependence of resistivity, we first of all saw for metals and alloys, the difference between the metals and alloys. Alloys basically two or three metals mixed together. For metals, we saw that the graph was parabolic, right? Resistivity versus temperature. But for alloys, we saw that this graph is actually a straight line graph. That means both these graphs show that alloys have a relatively smaller temperature coefficient. That means at a greater value of temperature, at a higher temperature, for same amount of change, at a higher temperature, for every 1 degree change in temperature, the resistivity of metals will increase at a very high rate as compared to alloys. So it is always a wise choice to use alloys in case your temperature is going to be increased, right? At a higher temperature, the value of resistivity for alloys will increase at a constant rate, at a fixed rate. But in case of metal, it increases rapidly, right? Then we saw for semiconductors. For semiconductors, the formula was simply like the relation was simply opposite. For semiconductor, the graph somewhat looked like this. As you keep on increasing the temperature, the resistivity of the wire will keep on decreasing. And the third thing was electrolytes. The third was electrolyte. I will write over here. For electrolyte, we didn't have any graph or anything, but we had a relation. So the conductivity will increase or the resistivity will basically decrease. So for semiconductor and electrolyte, it is the same relation. The resistivity will decrease as the temperature will increase. Resistivity will decrease as temperature increases. The same relation, right? Then we discussed about two things like ohmic conductor and non-ohmic conductor. Conductors which obey Ohm's law are ohmic, conductor which don't obey Ohm's law are non-ohmic. In case of non-ohmic conductors, we saw primarily four graphs. The first graph was pretty simple. That was a simple linear device which actually had a non-linear component. This is sort of pure metal when it is heated at a very high temperature. Then we saw the graph for a, PN junction diode. For a PN junction diode, graph was something like this. For a PN junction, then we had a thyristor, somewhat like this. And the last was a gallium, your gallium arsenide. Gallium arsenide was more important. Why? Because it has a negative resistance part as well in its graph, right? Then we had superconductor. Superconductor is anything which actually loses its conductivity, loses its resistivity completely. That means like theoretically the resistance becomes zero. How can we achieve this thing? Whenever we cool down the conductor below a particular critical temperature. Grouping of resistance, I'm sure everyone must know this formula. That series, you will just keep on adding the resistors, and for parallel it will be 1 upon R1 plus 1 upon R2 and so on, as many number of resistors as you have. And then the later half of the chapter was on EMF. The later half of the chapter was on EMF. EMF was basically, so it is not a force, it is actually the amount of work done. But EMF is the work done in open circuit. Just need to remember these two things, especially for your statement based question. EMF was the work done in open circuit, while terminal potential difference was work done in closed circuit. Work done by a cell or a battery, right? Relation between EMF and your terminal potential difference was basically V is equal to E minus IR. Small r was the internal resistance, E was the EMF of the cell. From now on, what we used a cell like this. Every cell will have a internal resistance and some EMF. Capital R we always used for our external resistor, right? So this was the relation between terminal potential difference and our EMF. Then we saw the formula for current. So current will basically come out to be E minus V by R, or instead of V I can write E minus I into capital R by R. Then we saw again three graphs. First graph was for EMF versus external resistance. Value of external resistance does not have any effect on the EMF. It remains constant. The third graph was for terminal potential difference versus external resistor. This graph was something like this. At this value, when the value of external resistance is equal to internal resistance of cell, it is equal to E by 2, half of EMF. And then it achieves a constant value. And the third graph was for V versus I. VI graph, this was a straight line graph with a negative slope, and slope of this graph was equal to minus of R, minus of internal resistance. Then we studied combination of cells. Combination of cells if the cells are grouped in series and grouped in parallel. In case of series grouping, we saw the total EMF is simply calculated by adding respective EMFs, and total resistance is basically, formula for resistance remains same, R1 plus R2 plus R3 and so on. But for parallel, what happens is that for parallel, the formula for this EMF, net EMF, total EMF is slightly changed. EMF equivalent by R equivalent is equal to E1 by R1 plus E2 by R2. And the formula for resistance remains same. Total resistance in parallel, or R equivalent, 1 by R1, 1 by R equivalent is equal to 1 by R1 plus 1 by R2. Okay, this was for series and parallel. And then we said that if all the cells are identical, then how will these formulas change? So if all the cells are identical in series, our total EMF becomes, equivalent EMF becomes n times if you are using n number of cells, and total resistance becomes in series n times of R. In case of parallel combination, your equivalent EMF remains same, equal to E, and your total resistance becomes R upon M. You're using n number of resistor in series, m number of resistance in parallel. And then we had something called as mixed grouping. Third was our mixed grouping. Mixed grouping means we have n number of cells in series and then m number of such rows in parallel. Total we have m into n number of cells, that is mn number of cells, right? So now in over here we need to find out that when can my current will be maximum. The formula for current in this case came out to be mne upon mr plus nr, and for maximum current the condition came out to be as, for current to be maximum, your total external resistance should be equal to nr by m. This was the main result of this complete exercise. Then the next topic which we had was heating effect. Heating effect, or Joule's law of heating. Joule's law of heating basically suggested that the amount of heat or amount of energy released will always be equal to I square RT. I is the current, R is the resistance, T is the time for which current is flowing through the resistor. Then you can find out this is the formula, and you can just interconvert it. Like the formula can also be v square by r into t, or it can also be v into I into t. And you can calculate power by energy upon time, or heat energy upon time. So for power also we had three formulas: I square r, vi, and v square by r. Power is always calculated in watts, energy is always calculated in joules, time is kept in seconds. Then commercial unit of energy consumption is, commercial unit is kilowatt hour. Commercial unit is kilowatt hour, and 1 kilowatt hour is basically equal to 3.6 into 10 raised to the power 6 watt second, or joules. Watt second is simply joules. Okay. So kilowatt hour, basically when we take power in energy, is power into time. If I take my power in kilowatt and time in hours, kilowatt, the relation between 1 kilowatt and watt is 1 kilowatt is simply 1000 watts. 1 hour is basically 60 minutes, or it is also equal to 3600 seconds. This is how the conversion has been done. And then there were some applications of heating, right? Then we had Kirchhoff's laws, one of the again most important topics. We had two laws. First was KCL and second was KVL. You just need to remember a few facts. KCL, basically not loop. KCL is also called junction rule. It is applicable over a junction. It basically says that the total current will always be zero at a junction. That means input current will always be equal to the incoming current will always be equal to the outgoing current. Now this law or this principle works on the law of conservation of charge, because it works on this principle that whatever amount of charge comes inside any junction, that same amount of charge will be will go outside the junction, because charge is conserved. Charge can actually not get lost in the process. KVL, also called loop rule, it says that whenever you move in a closed loop, whenever you move in a closed loop, net potential should always be zero. That means there must be a battery which must be supplying the potential. Whatever potential, total potential is that this battery is supplying, only that amount of potential can get distributed within the circuit elements, right? This principle or this law works on the law of conservation of energy. It works on this principle, right? Based on these two laws, we had studied something called as a Wheatstone bridge. Wheatstone bridge, or I should say balanced Wheatstone bridge. Balanced Wheatstone bridge says the ratio of the resistances should be equal to like balance. Wheatstone bridge setup is something like this. In the middle we had galvanometer, and this whole setup was connected to a battery. If this is P, this is Q, this resistor is R, this is S. This was the balance condition, and under balance condition, current through the galvanometer will be zero. That means we can just simply remove this middle branch. This was the balancing condition, and based on this balancing condition of Wheatstone bridge, we had meter bridge. Okay, so for meter bridge there was only a single formula for meter bridge, that your unknown resistance can be calculated by the known resistance multiplied by 100 minus L upon L. I'll write it over here. Unknown resistance S is equal to known resistance R multiplied by 100 minus L divided by L. L is basically the length of the wire at that till that point where you find out the balance point. Okay. So this was the end of current electricity. Now moving forward, we'll discuss both the chapters of magnetism together. We are just going to discuss the formulas. So for magnetism, we just started our discussion by understanding what do we mean by magnetic field, an area surrounding a magnet in which any other magnetic material will experience a force. Force can either be attractive or be repulsive. Now, the magnetic force which acts on the charged particle is Q V cross B if I talk about in the vector form, and if I talk in scalar form, it will be equal to Q V B sine theta. Magnetism will only be experienced by a moving charge. Electrostatics will always be experienced by a static charge, right? So whenever a charged particle is moving with some velocity v in some magnetic field B, it will experience a force which can be calculated by qvb sine theta. Theta is the angle between velocity. For example, particle is going in this direction, magnetic field is in this direction. Now this will be your theta. So force will be maximum at an angle of 90 degree. Force will be minimum at an angle of 0 or 180 degree. Because at 0 and 180 degree, sine 0 and sine 180, the value is 0. Now coming to magnetic field, the magnetic field unit is Tesla. SI unit is Tesla. Unit can also be Gauss or Weber. Okay, Weber per meter square. Moving forward, then we had two laws in this chapter. First is Biot-Savart law. Biot-Savart's law. Biot-Savart's law basically told us that, the name of this law is also called Laplace law. It basically told us that the small amount of magnetic field acting on any particle is mu naught upon 4 pi I dl cross r divided by r cube. I dl cross r divided by r cube. This is the formula which Biot-Savart law gave us, and using this law we had calculated the magnetic field at the center of a current carrying coil. For a coil, at the center of a coil, the field came out to be mu naught upon 4 pi 2 pi n I upon r. N is the number of turns in the coil, right? So you can just simply say we haven't cancelled 2 pi with 4 pi deliberately, because mu naught upon 4 pi, the value of this complete term is 10 raised to the power minus 7. It is comparatively easier to convert. If you want, you can cancel it out, not a problem. Okay. Then the second application was calculating the magnetic field due to a long current carrying conductor at the end of the long current carrying conductor, right? So the formula for that was mu naught upon 4 pi I by A sine phi 1 plus sine phi 2. Phi 1 and phi 2 were the angle made by the point with the two ends of the wire, right? Then the third thing was, this was for the center of circular coil. Then the third application was at a distance from coil. This is a coil. We are saying we need to find out the field over here at a distance. Coil from at a distance. The formula for magnetic field then came out to be, in this case, field was equal to, I'll just write the scalar formula, mu naught I A square upon 2x square plus a square raised to the power 3 by 2, right? And then you can say that a is basically your radius and x is the distance between the point and the center of the coil. So then we can make some special cases that if the value of x is very greater than a, then you can just ignore a in the denominator, and then in that case your formula becomes b mu naught I a square upon 2 x cube. Okay, then at the center of the coil, the value of x will be 0, and you will get the same formula which is written at the bottom. And if this coil has n number of turns, you will just simply multiply this formula by n if the coil has n number of turns. This was Biot-Savart law, and then the other law was Ampere's circuital law. Ampere's circuital law. Ampere's circuital law, basically it is a analogous of Gauss law. It said integration of B dot dl over a closed loop will always be equal to mu naught into I. Mu naught times the current passing through that coil. Okay. Then using this law, we had two applications, first for solenoid and second for toroid. For solenoid, our magnetic field came out to be B is equal to mu naught n I at the like for the inside the solenoid, and at the poles, or at ends, not poles, at ends of the solenoid, formula was just half, like field strength is just half mu naught n I by 2. Then the second application was for a toroid. For a toroid, formula was same, B is equal to mu naught n I, right? And then there was something called as so we already discussed magnetic force, and we already discussed electric like the electrostatic force. If both these things are experienced by a charged particle simultaneously, then we call it Lorentz force, and both these force gets added. Lorentz force is QE. QE was the electrostatic force, and V cross B was the magnetic component. Okay. And then you get questions like, whenever a charged particle is entering the magnetic field, what distance will it cover, in which path will it travel, right? In which path will it travel? So whenever the particle travels at a 90-degree angle, it will always go in a circular path, and for that circular path the radius will be mv upon qb. And then you can also calculate the time period, the frequency of that charged particle. Okay. Now moving forward to two important things, like from your point of view for formula. First thing was force between two infinitely long wires, current carrying wires. What will be the amount of force? So force will basically be mu naught upon 4 by 2 I1 I2 by R. R is the distance between the wires. And the other thing was force experienced by coil placed in field, in an external field, like this, something like this. You had a coil, and this was kept in a field. It was experiencing a sort of a torque. So we want to find out the total force. Force was simply BIL, and it will also experience a rotating tendency. That means a torque. Torque was simply M cross B. Value of N was NIA. M was NIA. We'll discuss these things in the this magnetism and matter. So M was basically the pole strength in case of a magnet, right? Pole strength of the dipole moment, magnetic dipole moment. Now the last and most important device of this chapter was MCG, moving coil galvanometer. So you people must be aware about the principle, and like, why is the magnetic field radial? So it is radial so that the direction of electric field or the intensity remains constant in all directions. So for MCG there were 3-4 formulas. First, for the sensitivity, current sensitivity was basically theta by I or NAB by K. Then second formula was for voltage sensitivity, that was current sensitivity divided by resistance of galvanometer, or NAB upon K divided by RG. RG is the resistance of galvanometer. Then there were two things, conversion of MCG to ammeter and conversion of MCG to voltmeter. For ammeter, we used a shunt resistor in parallel, and the formula, the value of that shunt resistor should be Ig into G divided by I minus Ig. And the formula for this resistance of ammeter, the resistance of ammeter will be Gs upon G plus S. G is the resistance of galvanometer, S is the value of shunt resistance. Then MCG to voltmeter. MCG to voltmeter. our resistance will be V by Ig minus G. Okay. So this was the main part of MCG. Now coming to the magnetism and matter chapter, first like you studied the basic terms. What do you mean by magnet? What do you mean by poles? There are two poles, north and south. Opposite poles will attract each other, like poles will repel each other. Then there were things similar to our electrostats, right? Jesse, like the very first thing was magnetic dipole moment. So magnetic dipole moment similar to electric dipole moment was pole strength, or we are saying QM means magnetic pole strength multiplied by the length of the magnetic dipole. That means length of the bar magnet. Then we had formula for axial and equatorial point. In electrostats, we had formula 2 kp by r cube and kp by r cube. Over here, we'll have formula for axial point mu naught upon 4 by 2m by d cube. And for equatorial point, formula will be mu naught upon 4 by m upon d cube. Okay, these were the two formulas for axial and equatorial point. Then we had the formula for torque, just like we have in electrostatics. Whenever the electric dipole was kept in a uniform electric field. Now we are saying a magnetic dipole kept in uniform magnetic field. Formula was m cross b. Formula for potential energy was minus m dot b or mb sin theta. The formulas are exactly same. Then there were four things, four particular terms. First was magnetic induction. Magnetic induction was basically the amount of magnetism which can be induced in a substance, right? Then in terms of formula or numericals, if I talk about, there was something called as intensity of magnetization I, and that intensity of magnetization was basically magnetic moment per unit volume. Magnetic moment per unit volume. Magnetic moment is your Qm into 2L divided by volume is area into 2L, right? So that was also equal to pole strength divided by the area per unit area. This was intensity of magnetization. Then we had magnetic intensity. The symbol for magnetic intensity was H, and the formula was B is equal to B naught is equal to mu naught H or mu naught N I, right? The formula for H was B upon mu naught minus I. This was the vector formula. And the last thing was magnetic permeability, mu. Mu was basically equal to B by H, magnetic permeability. And then there was something called as relative magnetic permeability. Relative magnetic permeability mu r was simply mu upon mu naught. Okay, so like magnetism and matter was a relatively very small chapter, and there were three types of substances: paramagnetic, ferromagnetic, and diamagnetic. You should remember at least four properties for each, the main properties that can actually come as a statement based question. Okay, so this brings us to the end of magnetism. Now moving forward to EMI and AC. EMI and AC. EMI is basically electromagnetic induction, and we first studied what do we mean by magnetic flux. Magnetic flux was basically B dot A, dot product of magnetic field with area. And there was first two laws. First law for Faraday gave two laws: Faraday's first law and Faraday's second law. I'm just going to discuss all the formulas, keeping in view the time constraint. So EMF was basically, Faraday's law stated that EMF will basically be equal to the negative rate of change of flux with respect to time. E is equal to minus d phi by dt. Why does a minus sign exist over here? This minus sign was explained by Lenz's law, that the reason due to which this EMF was induced, this EMF will always oppose the reason which induced it, right? So the things will always start in happening the opposite direction. Then we had the very next thing was induced potential difference or induced EMF. Induced EMF in a rod. So in a rod, induced EMF, the formula was E is equal to BLV. L was the length of the rod, V was the velocity with which the rod was moving. And there was also a proof, like this was also counted as a proof of Faraday's law, right? And from the point of view of NEET exam, very important formula, field across a rotating bar. This is a bar, it is hinged at one end and it is revolving, it is rotating in this circular path. What will be the induced EMF? So induced EMF will be minus, sorry, not minus, half B omega L square. L is the length of this rod or the radius of this circular path. Omega is the angular velocity with which it is rotating and B is the magnetic field. So there is this magnetic field inside the plane. Okay, now you need to remember two things. The question does not come straightforward from this part, especially. This formula, which says E is equal to minus half, sorry, E is equal to half B omega L square. This gives you the EMF induced in the between the is two ends of the conductor, two end of the wire. Now, question might ask you that if this wire, if this rod is actually hinged in the middle, then what you will do? So for that, you should know the process through which this EMF was calculated. So we took small change in EMF is equal to BV into dr. We replaced V with R omega dr. Then we said if we need to find out the total EMF, we need to integrate. So we integrate on the other side. This becomes EMF and we integrate on the other side. B omega comes out of the integration as that is a constant. We integrate R with respect to dr and we used a definite integral. When we need to find out from for the complete rod, we took initial point as 0 and that final point as L, 0 to L. Now if you need to find between this point and this point, you can simply take from R by 2 to R. You just need to change these limits according to the point at which you have hinged the rod, right? And then you will be able to get the correct formula. Okay. Then moving forward, there were two phenomena. First was self-induction and the second was mutual induction. So self-inductance was the formula for the symbol for self-inductance was L and phi is equal to Li was the formula. We calculated self-inductance and if phi is this, EMF is equal to minus L di by dt. Then we calculated the self-inductance of a long solenoid. In case of a solenoid, self-inductance was mu naught n square A L. Mu naught n square A L. N is the so small n is basically used for per unit length, right? Or per unit this thing. Capital N is basically used for the total thing, right? This was for a solenoid. Moving forward, then next we have energy stored in a inductor. Energy stored in a inductor. Energy in an inductor is basically half L I square, right? Then we had mutual induction. Mutual induction when change in EMF of first coil induces a EMF in second coil. Formula for mutual inductance was similar. Phi is equal to Mi. EMF is similar minus M di by dt. Then we calculated the same thing for solenoid. We have two solenoids connected with each other, like kept like this. This was the first solenoid and then this is the second solenoid kept like this. What will be the mutual inductance? So mutual inductance was mu naught N1 N2 AL. You always have to take the area of smaller solenoid. Like over here, when we derived this formula, we considered the area and length of both the solenoids are same. But in case for two solenoids, you are given two different values. Always take the area of the smaller solenoid and always take the length of the bigger solenoid. That means area has to be small and length has to be large enough, right? So this was all about your EMI chapter. And there was one more thing, which is like you might get a numerical based on that you have a moving wire, the moving wire experiment, which was actually performed. And in this, they might ask you that you're moving this rod with a velocity v over a U-shaped frame. What will be the resistance? What will be the current? What will be the force? What will be the power? So the formulas for all these things was current was basically BLV by R, BLV by R. Power was B square L square V square by R. Force was B square L square V by R. Okay. So these three formulas, these were not mentioned anywhere like in the book directly or something like that, but this was something which we derived while understanding the process. But numerical questions do come from this part directly. Okay. So this was our EMI chapter. Now moving forward to AC. So in AC, we basically discussed about a different type of current which was alternating. The name of which was alternating current. Alternating current, a current which changes its value after fixed intervals like this, like a sinusoidal wave or a cos wave. So the general formula for like a sine wave can be used to represent a AC current, I naught sine omega t, or E is equal to E naught sine omega t. Right, I naught and E naught are the maximum values, the peak values. Omega is the this your angular frequency, and T is the time instant. Then first of all, we calculated two things: mean value or the average value of current, and the RMS value. RMS means root mean square. So average value of current came out to be 2 I naught by pi. That means 0.637 I naught. This is approximately that the average value will be achieved. Average value will always be equal to 63.7% of the peak value. Then RMS value is simply I naught by root 2. I naught by root 2, or simply 0.707 I naught, or we can say 70.7% of the peak value of current. Then you saw there were like different combinations. If you have a purely resistive circuit, you have a purely inductive circuit, you have a purely capacitive circuit. You need to draw the phasor diagram and the formulas, right? I'll just, so we'll do it on the next page. If my circuit is purely resistive, for a resistive circuit, current is I naught sine omega t. Current and EMF are basically within same phase. In case of resistive circuit, our phasor diagram looks something like this. This is I naught, this is E, for a purely resistive circuit. Then for a purely inductive circuit, if current is I naught sine omega t, for inductive circuit, we need to use the formula E is equal to L di by dt. Okay. So EMF is basically, EMF comes out to be over here I naught, sorry, E naught, or I will first write this formula. I naught upon this thing. E naught, I naught into omega L. Omega L is basically XL, inductive reactance, XL, and then the same thing, sine omega t plus pi by 2. This means if my current, the phasor of my current is over here, then EMF is over here. So EMF basically leads by an angle of 90 degree, pi by 2. EMF is ahead of current by 90-degree angle. In capacitor, for a purely capacitive circuit, the case is just opposite. I is equal to I naught sine omega t. So for this, you just need to use I is equal to C dV by dt. EMF is I naught upon omega C sine, I'll write it above. For capacitor, I am writing over here I naught upon omega C sine omega t minus pi by 2. If current is here, then EMF is behind the current by an angle of 90 degrees for a purely capacitive circuit. XL and XC, this thing 1 over, write it over here, 1 over omega C is basically capacitive reactance. Okay, and then we had something called as a LR circuit. That means LR circuit has a inductor and a resistor. For a LR circuit, our phasor looked something like this. This was VL, this was VR. Net EMF was somewhere in between. And the value of total impedance Z was simply root R square plus XL square. And you were asked to calculate this phi. This tan phi was equal to XL by R or omega L by R. Similarly, we had a CR circuit. In CR circuit, this is VC, this is VR, EMF is somewhere here, and this is phi. Z is root R square plus XC square. Tan phi is XC by R or 1 over omega C R for a CR circuit. And then last we had LCR circuit, one of the most important circuit. For LCR circuit, I'll just write tan phi. Tan phi was basically if XL is larger in value than the XC circuit, like the XL component is greater than XC, XL minus XC by R, and total impedance will be calculated by root R square plus XL minus XC whole square. Within LCR circuit, there can be three possibilities. We have two things, XL and XC, which are opposing each other. So three possibilities can be: XL might be greater than XC, XL might be smaller than XC, XL might be equal to XC. Greater than, equal to, greater than and smaller than condition is catered over here. XL is bigger, we keep XL minus XC. XC is bigger, we keep XC minus XL within the formula. Within diagram, it will, if XL is bigger, the net EMF will, the net potential will remain in the upwards. If XL is smaller, XC is bigger, it will be in downwards. VR is always in this particular direction only. Okay, this is VL minus VC, this is VC minus VL. Though these two scenarios are catered over here, but the third scenario in which we are saying XL is equal to XC, this particular condition is called resonance or resonant condition. Resonance. Resonance is basically a condition when the impedance is very small. Z is small, impedance is small, and current is maximum. Now, using this concept of resonance, you are many a times asked to calculate the resonant frequency. So, resonant frequency is equal to 1 over root LC. Okay, this is angular frequency of resonance, and frequency of resonance nu is equal to 1 upon 2 pi root LC. Okay, then there was something called as a quality factor Q. Q was simply 1 upon R root L by C, quality factor, right? And then our power, the formula for power was ERMS IRMS cos phi. Cos phi, this term was called power factor. Okay, so like we have broadly discussed our alternating current AC chapter. Now moving to the last chapter, that is electromagnetic waves, like the last chapter of the first book. Electromagnetic waves, in electromagnetic waves you just need to remember some important things only. It is a comparatively smaller chapter, EM waves. For EM waves, you need to remember there are two currents, displacement current and conduction current, and both these currents are always equal in the value. Then you need to remember certain properties of the electromagnetic waves. Only and only from there the question usually comes. In general, the general formula, general form of electromagnetic wave, for example, for electric field is E naught sine omega t minus kx. Somewhat similar to what you have studied in oscillations and waves, omega t minus kx. You need to remember certain properties and certain values. The electromagnetic wave will always move with the velocity. If it is moving in air, its velocity is calculated by 1 upon epsilon naught, 1 upon mu naught. If it is moving in some medium, you just need to multiply mu naught, mu r, epsilon naught, epsilon r. Just this small change, right? And then the second thing from the numerical point of view, you need to remember the energy. Energy in electric field is half epsilon naught E square. Energy in magnetic field component is B square by 2 mu naught, right? And if you will see this, both these energies are equal in magnitude. We can just prove that. Okay, so total energy is basically the sum of both these things, and total energy comes out to be somewhat like epsilon E square or B square by mu naught, basically the twice of any of these. For EM waves, you just need to remember these many formulas and you will be good to go for your, especially for your numericals. Okay. Now, moving forward to our biggest unit called optics. I'll just give you guys also a break of 1 minute and then we'll resume with optics. Okay, so now we'll resume. So first of all, we'll see what do we mean by a mirror. Like I'm not discussing the pretty basic terms. For spherical mirror, we saw two formulas. First was the mirror formula 1 by u plus 1 by v is equal to 1 by f. And the second formula was for lateral magnification, which is hi by ho or minus v by u in case of spherical mirror. And I'm sure like in case you any of you has any doubt in the sign convention, then you can post your doubts in the comment and then I'll discuss it. Otherwise, I'm skipping it for now. Then similar formulas for spherical lenses. Spherical lenses, lens formula was 1 by v minus 1 by u is equal to 1 by f. Lateral magnification hi by ho or plus v by u. Now, okay, these were the two things which we discussed in the reflection of light and two laws of reflection. First law says that angle of incidence is equal to angle of reflection. Second law says incident ray, reflected ray and normal all lie in the same plane. Then we discussed refraction. Within refraction, we discussed two formulas. First was for refractive index, calculating the refractive index. Refractive index basically mu2 by mu1 is equal to sine I by sine r, or in case of, if I talk about velocities, v1 by v2. Okay, this was the first formula. Second formula was for depth. So if you have dipped something in water, or if I am talking about a swimming pool is filled with water, what will be the apparent height or apparent depth of the pool which will appear to you, right? Pool is actually 7 feet deep or 5 feet deep, but if you look at the pool standing outside of it, you will feel that it is not actually 5 feet, it is lesser than that. So what will be that apparent depth? So mu is equal to simply real depth by apparent depth. Real depth by apparent depth. Okay. And within rectangular glass slab, there was the lateral shift. The value of lateral shift can be calculated by 1 minus 1 upon mu into T. T is the this thickness of glass slab, or this was the glass slab, so T is this side length, okay, not the thickness. So within refraction, we discussed these formulas. Then for prism, for a rectangular prism, we discussed three formulas. First of all, angle of deviation. Angle of deviation is basically I minus I dash minus A. A is the angle of prism. Minimum deviation formula is mu minus 1 into A, angle of minimum deviation, right? These were the formulas which we discussed for prism. Then we discussed something called as TIR, total internal reflection. TIR was basically a situation wherein the light is totally internally reflected. And within TIR, we discussed that at a critical angle, when incident angle is equal to critical angle, at critical angle, angle of refraction, like light will not actually emerge out, it will actually graze at the surface. This is the surface. If we incident the light ray at a critical angle, light will not actually emerge out, it will actually go in this direction. So at a value of critical angle, angle of refraction is 90 degree. Two conditions for TIR were, first of all, the value of the value of angle of incidence should be greater than the critical angle. Second main condition was that light ray must travel from a denser medium to rarer medium. Only and only in that particular scenario, TIR may occur, right? If the light is traveling from a rarer medium to denser medium, then TIR won't occur at all. Then we can say, if I want to calculate the critical angle, then this will be equal to, this will be equal to, I will simply write it like this. Mu is equal to 1 over sine IC. Okay. Mu is equal to 1 over sine IC. 1 is simply your sine 90. The value of sine 90 is 1. Why is the formula now inverted? We are saying the first medium now is the medium with refractive index mu. Second medium is air, if suppose. Then this formula is used for calculating the critical angle. Then moving forward from critical angle, we saw a lens maker formula. Lens maker formula. For lens maker formula, we discussed that lens maker formula is actually 1 by f is equal to mu2 by mu1 minus 1, 1 by r1 minus 1 by r2. R1 and r2 is the radius of curvature of the spherical surfaces, right? If your first medium is air, this mu1 becomes 1 and mu2 becomes mu, right? This was the lens maker formula. Apart from lens maker formula, we saw refraction through spherical surfaces. Refraction through spherical surfaces. Within refraction through spherical surface, we saw a formula. Formula was mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r. Whenever a refraction occurs through any spherical surface. Spherical surface means something like this. Refraction occurs from, light comes from here and then it gets refracted in some or the other way. This is mu1, this is second medium, this is first medium. And now we want to find out, u is basically the distance, object is kept over here, u is basically the object distance, v is the image distance. So this was the formula for that case. Then the last thing was power of lens. So power of lens is basically 1 upon focal length, and power of combination of lenses is simply the addition of power of individual lenses, or 1 upon f1 plus 1 upon f2. Just remember, we can never ever add the focal lengths directly. Only powers is additive in nature, right? Then the later half of the chapter had optical instruments. We saw particularly three instruments: simple microscope, compound microscope, and a astronomical telescope, right? So for a simple microscope, the formula was like pretty simple. We will discuss just for the simple microscope question don't usually come. Compound microscope. Compound microscope, the magnification was 1 plus d by f e, right? This was when the image was formed at a near point. At near point. If the image is formed at infinity, then the magnification will become d by f e. If the image is at infinity, then we had two things called in within astronomical telescope: near point, normal adjustment and least distance of distinct vision, right? So for normal adjustment, formula was v by u d by fe. This was for normal adjustment, and magnification becomes v by u 1 plus d by fe, or 1 by fe 1 plus d by fe in case of least distance of distinct vision. This whole thing is for a astronomical telescope. Okay, astronomical telescope. These were the three main optical instruments which we studied. Then moving forward, coming to wave optics. Within wave optics, first of all, we studied about wave. What do we mean by wavefront? Then what do we mean by Huygens principle? And for Huygens principle, like what are the two pointers of the Huygens principle? Moving forward, then from the Huygens principle, we studied about refraction and reflection of wave, right? Then we saw two experiments, like from the point of view of numericals. First was Young's double slit experiment, and second was your diffraction. For Young's double slit experiment, first of all, we saw a formula for calculating the fringe width. Fringe width was capital D by small d into lambda. Capital D is the distance, small d is the distance between screen and the light source. Capital D is the distance between the two slits. Lambda is the wavelength, right? And then the distance between bright fringe and the central fringe is basically n d lambda by d. D is the distance between source and the screen, right? And lastly, we saw the formula for path difference. For bright fringe, For bright fringe, path difference is equal to n lambda. For dark fringe, it is equal to n plus 1 by 2 lambda, right? And then we saw diffraction. In diffraction, we saw a condition which says b sine theta should be equal to n lambda for a dark fringe. Then width of the central maxima. Width of central maxima is 2 lambda by b. Angular width is 2d lambda by b. Okay. These were the main important formulas. And then we had polarization and interference of light. Interference basically, for interference, you just need to remember two formulas. First, the total intensity. Intensity is just root I1 plus root I2 square. The square root of individual intensity is the sum of those and the whole square. And this can also be equal to beta A1 plus A2 whole square. A1, A2 are the amplitude. Amplitude of a wave is always directly proportional to root of intensity. Just remember this. Then for constructive interference, A is A1 plus A2. Amplitudes get added. For destructive interference, A is equal to A1 minus A2. Okay. For interference, you have just these two formulas. Then moving to our modern physics. Within modern physics, the very first chapter was dual nature. For dual nature, there are two primary concepts. First is the photoelectric effect, second is the de Broglie hypothesis. Okay, so we discussed what do we mean by photon, and photon will always move with the velocity speed of light. Then within photoelectric effect, you just need to remember the Einstein's photoelectric equation and laws of photoelectric emission and the graphs. So first we'll discuss the graph. First graph is for photoelectric current and intensity. Photoelectric current and intensity graph is a straight line graph. That means as you increase the intensity, the current will increase. Then the second graph was, the next two graphs were similar in the sense that both these graphs are between current and potential, stopping potential, photoelectric current and stopping potential. One graph is for a constant intensity, one is for a constant frequency. So this first graph is for a constant frequency and different intensity. This is current. Constant frequency and different intensity. I2 intensity is greater than I1, frequency is constant. The second graph is for different intensity, different frequency and constant intensity. This is VO1 stopping potential, this is VO2. This is for frequency 2, this is for frequency 1, right? Frequency 2 is greater than frequency 1 over here, and intensity I is constant. And the last graph was between stopping potential and your frequency of radiation. This graph looks something like this, a straight line graph, and it starts with nu naught. Nu naught was the threshold frequency. Coming to the Einstein's photoelectric equation, I'll write the complete equation, all the formulas together so that it's easier. Kinetic energy is equal to E into V naught, basically charge multiplied by this charge multiplied by stopping potential. E into V naught is equal to H nu minus nu naught is equal to H C 1 by lambda minus 1 by lambda naught. Okay, so this is the complete formula. Kinetic energy, you can also write it as half mv square. You can be given any two things and ask the third thing, right? Like you can be given the velocity with which the electron is emitted. You should the mass of the electron will already be given, charge on electron, and you might be asked to calculate the stopping potential. So this V naught over here is the stopping potential. Stopping potential, basically the negative potential which has to be applied from the outside to stop the emission of electron, right? This was your photoelectric effect part, and within de Broglie hypothesis, you just have single formula, de Broglie wavelength, which is equal to h by p or h by mv. H is the Planck's constant, p is the momentum. And you also have a formula for calculating de Broglie wavelength of electron. So for electron, formula is 12.27 divided by root V in angstroms. V is the applied external potential. This is just for a electron and not for any other charged particle. Okay, only and only for electron. Then moving forward to atoms and nuclei. Moving forward to atoms and nuclei. Within atoms, you first study the Rutherford's model. Then within Rutherford's model, whatever observations and conclusions Rutherford made. Then the second thing was your the limitation of Bohr's model. Bohr suggests, sorry, not Bohr's, limitation of Rutherford's model. Rutherford said that electrons will always keep on emitting the some amount of energy whenever they are revolving along the outside the nucleus. The only problem with this concept was that if electron keeps on radiating the energy when it is revolving, there will come a time, so at a certain point of time, the net energy of this electron will become zero, and this electron should eventually fall into the nucleus. But Rutherford was not able to explain this thing. Then came Bohr. Bohr explained these things and they gave some postulates. So the most important thing from the point of view of your exam is Bohr's model or Bohr's postulates. The very first formula which Bohr gives was the angular electrons will not revolve in any orbit, but they will only and only revolve in those orbits whose angular momentum is an integral multiple of h by 2 pi. This was basically Bohr's quantization condition. Then he also told something related to these things electrons will always revolve in fixed orbits, and Bohr said that electron will never ever emit any amount of energy when it is revolving into a orbit. Electron will only emit or absorb some amount of energy when it will change its orbit, like if it goes from a lower energy state to a higher energy state, then it will need to absorb some energy. Whenever it will come from higher to lower state, it will release some energy. But energy in every orbit will always be fixed. And for that, he also gave some formulas. So I'll just write all the formulas quickly. For the radius of orbit was 0.53 n square by z Armstrong. I'm just writing the final formula, so you don't have to remember any sort of constants or anything. N is the orbit number of orbit. Z is the atomic number. Why am I writing the formulas with atomic number? Because atomic number. Bohr's model, Bohr explained and gave the complete model for hydrogen. But Bohr's postulates and Bohr's models are also extended to hydrogen-like species. Hydrogen-like species, what do I mean by that? The species which have a single electron, right? So hydrogen-like species also, it is applicable for those also. So Z is the atomic number. This is radius. Then we have velocity. With the velocity is 2.2 into 10 raised to the power 6 Z by N meter per second. Then we have potential energy minus 27.2 Z square upon N square EV. Then we have, this is potential energy. Kinetic energy is 13.6 divided by N square Z square EV. Kinetic and potential, and you can see kinetic energy is just half of the potential energy, and like plus half of the potential energy. Kinetic energy is equal to minus half of potential energy. Okay. So this is how you can also calculate the total energy. Out of these, if you're not able to remember all the formulas, you're facing some confusion. You need to remember this formula for radius and you need to remember this formula for energy. Like these are the two most commonly asked formulas. Then there was something called as a hydrogen spectrum or spectral series. So within spectral series, that if you want to find out the wavelength, the wavelength of which the light is emitted. So you can calculate the wavelength by like this wave number. Just change the color. Wave number is basically 1 upon wavelength. It is equal to R into 1 upon NF square minus 1 upon Ni square. Okay. And the spectral series, the very first was Lyman, then Balmer, Paschen, Bracket, and Fund. Lyman when your final shell number is 1, Balmer when it is 2, Paschen 3, 4, and 5. Okay. Lyman will always release in UV region, emission will be in UV, Balmer in visible region, and for these three, emission is in infrared region, right? You can just simply calculate the wavelengths. If you want, I can also give you the minimum and the maximum wavelengths. So I'll just write over here minimum and maximum wavelengths. Like for your easy reference, you can just remember these values. All these values are in Armstrongs. Okay. Mm, mm, mm. Change the color and yeah. So for Lyman, minimum is 912, maximum is 1216 Armstrong. Balmer, minimum is 3468, maximum is 6563. Paschen, minimum is 8208, maximum is 18761. Then bracket 14592, 40533. Then minimum over here is 23850, 74618. You don't need to remember all of these. You can just remember the first four numbers and that will just simply serve your purpose. Okay. Then in the very next chapter, that is nuclei, within nuclei, you need to just remember two things. First, the binding energy, the mass defect. Mass defect can be calculated by ZMP plus A minus ZMN minus M. M is the observed rate and this is the calculated mass. This is the observed mass. This is the mass defect. Then binding energy is basically delta M into C square. Binding energy per nucleon is simply binding energy divided by the atomic mass A. Okay. And then there are something like basic things called half-life, main life. Half-life is the time amount of time in which a substance becomes half in its concentration, right? So that is half-life. Nuclei within nuclei chapter, you just need to remember these. Most important are these three formulas only. Okay. And then coming to our last chapter, that is semiconductors. For semiconductors, the first and foremost thing which you should remember is P-type, N-type semiconductor. What do you mean by that? What is the difference between them? What is the PN junction diode? Or what is a PN junction? What is a PN junction diode? And the phenomena involved in PN junction diode. Two main phenomena, diffusion and drift. You can get a theory based question or a statement based question from this chapter. And this chapter is very, very, very important. The two main phenomena, diffusion and drift. And then the graph. VI graph of a PN junction diode and biasing, forward biasing and reverse biasing of a semiconductor, right? Then you should remember three most important devices: light emitting diode, LED, photodiode, Zener diode. Okay, Zener diode is basically used as a voltage regulator. You should remember only these many things. There are no particular formulas or anything, but there are theory based questions and concept based questions which might come from this chapter. Okay, so if we just once go back and see what all we have discussed today, so you can see we just started from electrostats. Within electrostats, we started with our first chapter, that is electric charges and field, and we discussed all the properties, Coulomb's law. Then we came to then we discussed the principle of superposition, electric dipole, electric field at axial and equatorial point of a dipole for a ring. Then we move forward and okay, so next page we had grouping of capacitors. That is what we discussed in the electrostats, then current, electricity, and so on. So, like I've tried to discuss as many things as possible, but given the time constraints, and this is supposed to be a revision marathon, so there are some limitations like on the number of things which we can actually discuss over here. So, a very important part, like the revision is actually done from my side, but what you have to do is you can also check out the shorts and the other videos which we are actually posting, wherein we are all the teachers are sharing, some short tricks and tips for you people, how you can speed up your calculation in your exam, and how can you actually like benefit maximum, right? And try and score as much as possible. So just check those things also out. And we have in fact also shared some tricks that how to avoid losing marks in negative marking, right? Do make sure that you revise the high weightage chapters. So if I tell you the high weightage chapters from the class 12 syllabus: electrostats, current, electricity, modern physics, and semiconductors. These are one of those chapters which are easy, like comparatively easier. I would say like EMI and AC is as important. But the problem is many students are not really comfortable in solving EMI and AC questions, numericals, because they are sort of tricky, somewhat tricky. Like you have to have a very good understanding to solve those numericals. Otherwise, EMI and AC also have a good weightage. But if I am talking about some parts which are easy to score and have a good weightage, so these are electrostats, current, electricity, modern physics. Within modern physics, dual nature, atoms and nuclei, and semiconductors. If you do at least these, you will like, I'm just sort of telling these chapters and keeping in mind that you only have 1 day left for your exam, and you need to make the most out of this time, right? From class 11 syllabus, don't forget to revise units and dimension, kinematics, work energy power, laws of motion, and then in the second book, your thermodynamics. Like these are the most important topics. So I've just told you 10 to 12 most important topics. Make sure that you first complete the revision for these 12 topics for your exam. And then if you are left with some amount of time, then you can discuss, then you can revise the other chapters in the remaining time, right? That won't be a problem. So I am sure that all of you are going to do really well in your exam. So don't worry about anything. Just keep yourself calm, and most importantly, sleep well. And because you should not be tired in the during the exam, right? Keep yourself hydrated. Just focus all your energy on the exam. Don't worry about other factors because they are not in your control, and I'm sure you will do really great in your exam, and you will get the desired results. Wishing you, all of you, a very best of luck for your exam. And thank you so much for staying in the class, and see you in the next video. I hope we'll meet after your exam, and I'll see some lovely comments wherein you will say that your exam went well, right? So looking forward to that. See you in the next video. Thank you so much.